and we'll start recording right now. Oh, someone said they can't hear me now. Can no one hear me?
I can still hear you.
Okay,
I have a question.
Yeah, go ahead.
So on Learning Suite, there's a second midterm 2 that says it's scheduled to open tomorrow. Is that?
Oh no, that's just junk. We looked into trying to do the midterm on Learning Suite. I need to delete that. And so I set up the midterm on Learning Suite originally, and I just set the day back so it wouldn't, so you guys couldn't see it yet. But I just need to delete that. That's garbage.
Okay, thank you.
Learning Suite ended up kind of crashing the week that the exam was, and so we ended up migrating everything over to WebAssign anyways. So I said this all a minute ago. Some of you were here probably at the last lecture, and that's fine. So a lot of this will be kind of repeat, but I'll say it anyways. So the exam will start on Friday. I'll have it open up at like 12:01 a.m. on Friday, so you can start it kind of first thing in the morning on Friday. It'll be open, I guess, until the exam window closes, which is, I believe, Wednesday night at midnight, I think, is the day that the exams close. Double check that. Whatever the official exam week is, that'll be when the exam is open. It'll be on WebAssign again. So it'll be a lot like the second midterm. It'll look the same as the second midterm. It'll be very similar. You'll have 5 hours to do this one. Again, the time starts the minute you log into the minute you open the assignment. So make sure that when you open the assignment, or when you open the exam for the very first time, make sure that you're prepared to sort of start taking the exam. Make sure you have your snacks and you have whatever available. I don't think it'll take most of you 5 hours. I don't think it'll take many of you 5 hours at all. It won't be much longer than the second midterm. So and I think people generally did okay with the time on that one. So it might have a question or two more, but not really anything beyond that. So again, it's on WebAssign, just like second midterm. Did I miss anything? Anyone have any questions on it that I didn't cover?
I just have a quick question.
Yeah.
So in terms of, like, I just can't remember from the last midterm, but in terms of like showing our work or anything like that, is there a way you're wanting us to submit any work?
So what we will do if you remember on the second midterm, for example, on the question when we asked you to diagonalize the matrix, okay? We gave a spot for the characteristic polynomial. We gave a spot for the eigenvalues and eigenvectors. We gave you a spot for the P matrix and D matrix and so on. And the way that we graded that is we didn't just look for the right answer at the end. The reason we have you do that is because if you put in your characteristic polynomial and then say you made a mistake factoring the characteristic polynomial, then you would get the wrong eigenvalues and you'd lose points on the eigenvalue part of that. But then if you use those incorrect eigenvalues to build the D matrix, we would still give you credit for the D matrix part because you made your mistake earlier on, but then you were kind of consistent after that point. So we'll have you sort of input your work at certain steps, certain checkpoints. And then when we grade it, we won't just sort of, that's why it kind of took a while to get the grading done, is because we had to kind of write the software to do that. But we won't just, we won't just look for the final answer at the end, or we won't even sort of just check give you different points for the different steps. If you make a mistake at one point on the exam and then but do everything correct after that point, we'll still have it set up so you get credit for that. So, but yeah, there won't be a place to sort of upload your paperwork or anything like that, if that's what you're asking. Is that okay?
Yeah, thank you very much.
Yeah. Other questions about the exam? It will cover everything in the course, though much of the course kind of is built up on the earlier stuff. So, it's really hard to sort of answer a question about, orthogonal matrices if you don't remember what it means to be linearly independent. So we won't ask too many direct questions from the earlier sections. We will ask a few. Most of the questions will be focused on the ladder material, but in order to sort of really get the ladder material, you kind of have to, you have to understand the earlier stuff anyway. So other questions?
How many questions are going to be on the test?
It will be, I don't remember exactly, it'll be similar to the length of the second midterm with a few extra questions. It won't be, I don't think it'll be dramatically longer than the second midterm. Like it might be 10% longer than the second midterm would be my estimation. And so I think what you can do is you can expect maybe like a 12 multiple choice questions, maybe a page worth of true false questions, and then something like 5 or 6 long answer questions. All right, anything else? I see a lot of flashing in the chat window. It's hard for me to kind of, I don't know how the chat window works with the recording, but if you have a question and you ask it in the chat window, I might not see it. So just unmute yourself if you do have a question. All right. Any other questions then before we go over these review slides?
Yeah, Dr. Hughes, is the final going to be curved at all?
Yeah. So the way that I don't curve individual assignments or anything like that. What we do is at the end of the class, I take all your homework and stuff like that. I take the weighted averages and I combine them into one final percentage. And then that's the percentage at the end of the class is what is curved. And so instead of just sort of sticking to the regular BYU cutoffs for what's an A, what's a B, what's a C, at that point, I'll sort of do some adjustments and I'll bump those cutoffs down potentially. In Math 313, we used to bump it down a reasonable bit just because I think the material in 313 included, students didn't tend to do quite as well in 313. Looking at the performance last semester, we didn't curve it quite as much just because the averages were quite a bit higher. This semester, who knows what it's going to be like with all the course disruptions. We will curve things. We'll never curve things up though. So we'll never bump the cutoff for an A or a B or whatever. We won't ever make the cutoff higher than it already is. But if anything, we'll make it a percentage or two lower to accommodate people who are right on the cutoff or something like that. But it's usually hard to predict exactly how much we'll cut it off, especially until we have all the final grades, especially this semester when things have been so unusual. I don't quite know what that process will be like right at the end or how much I'll be curving it, but there is some curving at the very end, yeah.
Okay, cool. Thank
And then you're all aware of the pass-fail option, right?
Yeah, we are.
Yes.
Yeah. Okay. Assume you're well aware of that. So that's something also to keep in mind. All right. Let's go ahead and let's talk about these review slides then. Again, feel free to just jump in and interrupt if you have any questions. These review slides are not meant to list off every single thing you have to know. I think they do cover a good. I think they are pretty comprehensive. I think they cover the big broad strokes topics you need to know. But within any of these topics I'm about to list, there's always sort of smaller parts, and I don't list all the smaller parts. So don't, if it's not something that directly shows up on this list, it doesn't mean you don't have to know it. But I think if this list gives you a good sort of comprehensive overview of what you should sort of be comfortable with going into the exam. So there's a little disclaimer just to sort of release me from any complaints that you might have about whether or not something shows up on this list. But here's the here's kind of the outline. So wait a second. I think this is okay. I think this is the fixed version. Yeah, go ahead.
Are these going to be posted?
Yeah, I will post these. I meant to do it in between classes, but the reason I was a few minutes late is I had to fix something that was on an error on the slides from earlier. So that's why I was a few minutes late coming to this chat. I will post them after this class before the noon class online. So chapter 1 was kind of all these introduction sections that we saw where we talked about a lot of topics, and they were all topics that kind of have shown up since later on in the course. So things like vectors, the dot product, orthogonality, norms, lengths of vectors, things like that. These are all things that we've seen since then. So I don't know if you probably won't spend a lot of time studying chapter 1 directly because a lot of these things show up later on. Chapter 2 is where we got into systems of linear equations. And when we give you a system of linear equations, there's kind of two questions you want to know, okay? There's kind of two questions that you want to know about any system of linear equations. The first question is there going to be a solution at all, okay? So you need to know, if we hand you a system of linear equations, how do you, by just looking at that system of linear equations, how do you tell whether there's going to be a solution? The second question you might ask is, when there is a solution, how do you know if that solution is unique, okay? So for systems of linear equations, there's three possibilities, right? You either get zero solutions, you get exactly one solution, or you get infinitely many solutions, okay? And so the first question is kind of, well, do you get zero solutions, or do you get more than zero solutions? The second question is like, well, do I get one solution, or do I get infinitely many, okay? And so the way we sort of study those questions, or the way we answer these questions, is by taking our matrix and row reducing it down to reduced row echelon form, okay? Once it's in echelon form or reduced row echelon form, you can look at the number of pivots. You can determine whether a solution is going to exist, or you can determine whether that solution is going to be unique. Then we introduced linear combinations. This was a topic that has come up again and again since that time. So remember, a vector y is a linear combination of the vectors v1 through vp if you can take the vector y and you can express it in this form here, right? Where the c's are scalars and the vectors v are the vectors that we're interested in, okay? So you should be able to take a vector y and a set of vectors v1 through vp, and you should be able to tell me, you should be able to, by sort of setting up an augmented matrix and row reducing, you should be able to tell me whether y is a linear combination of these vectors here. Then we introduced the topic of spanning, okay? And the big question here is, if I give you some vectors, how do you tell whether they span Rn? And then we introduced linear independence. And the big question with linear independence is if I give you a set of vectors, how do you tell if they're going to be linearly independent? So any questions on these ones so far? No? All right. So chapter 3 is where we got kind of into the nitty-gritty of things. So we talked about some matrix algebra. And in particular, we talked about inverses of matrices, okay? So as far as inverses of matrices go, you should know how to find the inverse of a matrix. And you should also know properties of matrix inverses. So for example, what would a property of a matrix inverse be that I'm talking about here? Well, suppose I have matrices A and B and I multiply them together, and then I take the inverse of the product. Well, this is equal to the product of B inverse A inverse, where I've had to swap the order, okay? So that's like one property of matrix inverses. And we saw a few others. So for example, I think like the inverse of A transpose is just equal to the transpose of A inverse, okay? So these are a few properties of matrix inverses, and there's a few others that you should kind of be comfortable with. We talked about the invertible matrix theorem. So remember, this was that big theorem that we came back to again and again. And this is that theorem that tells us that if you have a square matrix, it gave us a bunch of different conditions which were all equivalent to the matrix being invertible, okay? So this theorem had multiple parts, and I wouldn't necessarily go back and memorize all these parts per se. I mean, you should know them, but don't sort of memorize them as a list of different facts. What you should do is you should be able to sort of you know, if I tell you one thing about a matrix, like for example, the matrix has linearly independent columns, you should be able to sort of connect that fact to sort of being able to tell whether the matrix is invertible or not, right? So if a matrix has linearly independent columns, then you know it has a pivot in every column, and therefore it has to it's when you row reduce it down, it has to look like the identity matrix, which is the same as it being invertible. So there's, hopefully you can kind of see, like, you don't want to memorize it as a list of facts, but you should sort of be able to sort of jump from one to the other and sort of, you know, understand why one thing implies the other and so on. Okay. We talked about subspaces. So you should be able to sort of be able to tell when a set of vectors is a subspace. And you should be able to sort of, you know, then we talked about some examples like the row space, the column space, or the null space of a matrix. We talked about bases. So remember, bases are vectors that are linearly independent and they span a subspace. You should know how to find a basis for the row space, the column space, and the null space of a matrix. We talked about dimension. Now remember, the dimension of a subspace is just the number of vectors in a subspace. We also talked about coordinate vectors. We talked about the rank theorem. And then sort of the last big part in chapter 3 was all about linear transformations. And so how do you show that a transformation is linear? How do you find the standard matrix of a linear transformation? And then there's sort of a few different types of examples you might see. So any questions on all of this, kind of chapters 1 through 3, the first half of the course, more or less?
For dimension, if the only vector in there is the 0 vector, then the dimension is 0.
Yeah, that is correct. Yeah. So the only subspace of dimension 0 is the 0 vector, the 0 subspace.
Okay, thank you.
Yep.
Could we do a problem practicing checking if a given like set of vectors is a subspace? Like there was a test question that was kind of challenging, like mark all that apply.
Quite possibly I have one coming up for you. Let me just double check. I can't remember where I saw it. Well, maybe there's not one on this one. Yeah, I can come up with one. Let's go through the rest of these example slides, and then I will I'll create a list I'll create sort of a list off the top of my head of subspaces, and you can tell me if they're subspaces or not. So we'll kind of create an example on the fly here. Other questions there? Sorry. All right. So chapter 4 is where we got into eigenvalues and eigenvectors. So there's definitely like the algebraic definition of what it means to be an eigenvalue. So if ax equals lambda x for some non-zero vector x, then we would say that the vector x is an eigenvector and the vector lambda is an eigenvalue of the matrix A. Okay, so this is kind of like the algebraic definition. Then there is this geometric picture you should also sort of have in your mind, where an eigenvector is a vector, a non-zero vector x, so that when you multiply it by the matrix, you get instead of the vector rotating or moving at all, it just gets scaled. Okay, so this is sort of the geometric picture you should have in your head when we're talking about eigenvalues and eigenvectors. But you should also sort of be just as comfortable with the algebraic definition. Then we talked about eigenspaces. So remember, the eigenspace of an eigenvalue is just the subspace. Is just the subspace that's sort of spanned by the eigenvectors for a certain eigenvalue. So for example, if I have a matrix and I find that it has an eigenvector v1, you know, and this corresponds to say lambda equals 2, and then I have another eigenvector v2, and this also corresponds to lambda equals 2. So if I find like two vectors like this, then the eigenspace is just going to be the space spanned by these two vectors. So this is the eigenspace for lambda equals 2. Okay. So the eigenspace is just the, you know, if you take all the eigenvectors for eigenvalue 2, then look at their span, that's going to be the eigenspace for lambda equals 2. Now you should be able to find a basis for an eigenspace. In this case, remember, finding a basis for an eigenspace just comes down to finding the eigenvectors for that eigenvalue. So you just go through, we subtract lambda off the diagonal, we find a basis for the null space, and those vectors we get, those will always be a basis for the eigenspace. We talked about determinants. We computed them using cofactor expansion. We also saw some properties of determinants. So for example, if I take the determinant of A transpose times B inverse, well, you should remember that that's the same thing as the determinant of A transpose times the determinant of B inverse. And the determinant of A transpose is just the same thing as the determinant of A. The determinant of B inverse is just 1 over the determinant of B. Okay, so you should be able to take a determinant like this and recognize that you can kind of split it up and simplify it in this way. We learned about characteristic polynomials. We talked about similarity of matrices, and then we talked about diagonalization. And the big thing about diagonalization is first of all, can you diagonalize a matrix? That's one thing you should be able to do if possible. The other thing is you should understand sort of how do you tell when a matrix is diagonalizable or not, okay? And the question of whether a matrix can be diagonalized really comes down to comparing the algebraic and geometric multiplicities of each eigenvalue. So for example, if I have an eigenvalue, say lambda 1 is 2, lambda 2 is 2, and say lambda 3 is 0. Well, when I look for an eigenvector for lambda 1 and lambda 2, sometimes I might find 2 eigenvectors. So maybe I find v1 and v2, okay? So if I find 2 linearly independent eigenvectors, that means my geometric multiplicity was equal to 2. And because my eigenvalue showed up twice in my list, that means its algebraic multiplicity is equal to 2, okay? So in this case, the algebraic multiplicity and the geometric multiplicity are the same, and therefore I'm in good shape and I can continue on trying to diagonalize my matrix. If, on the other hand, I'd only gotten 1 vector, then my geometric multiplicity would be smaller than my algebraic multiplicity, in which case I know that I can't diagonalize my matrix, okay? So really answering the question of whether a matrix can be diagonalized comes down to knowing whether the algebraic multiplicity and the geometric multiplicity match, okay? Questions there? No? All right. So then we get into chapter 5. We did orthogonal and orthonormal bases. This is all more recent stuff, so I'll kind of go through this quickly. We saw orthogonal matrices. We had sort of certain properties of orthogonal matrices. So for example, if a matrix is orthogonal, then I know its determinant has to be plus or minus 1. I know that the eigenvalues have to have absolute value equal to 1. And for example, I know that that the transpose is equal to the inverse, okay? So these are some properties of orthogonal matrices, okay? We learned about orthogonal complements. So remember, this is if I have a subspace W and I look at all of the vectors that are orthogonal to W, that gives me W perp. That gives me the orthogonal complement of the subspace, okay? So any vector in the orthogonal complement is orthogonal to any vector in W, okay? And that's what it means to be an orthogonal complement. We talked about like finding bases of orthogonal complements. We talked about finding the orthogonal complement of the row space and the column space. So remember the orthogonal complement of the row space is equal to the null space of A. That was a fact we saw. We talked about orthogonal decompositions. So remember, that's where we take a vector y. We split it up into a piece that's parallel to W and a piece that's perpendicular to W. We did the Gram-Schmidt procedure. We talked about orthogonally diagonalizing a matrix. And remember, we have a question, the question of now whether a matrix can be orthogonally diagonalized. Remember, if you're just asking whether a matrix can be diagonalized, that's kind of a question that involves finding eigenvalues and eigenvectors and comparing the algebraic and geometric multiplicities. But when you ask whether a matrix can be orthogonally diagonalized, you don't have to check for any eigenvalues and eigenvectors. The only thing you have to do is you have to check whether the matrix is symmetric, okay? And if your matrix is symmetric, then it is orthogonally diagonalized. Then we talked about the spectral theorem, spectral decompositions, and then finally in chapter 7, we got into singular values, singular value decompositions, and the outer product form, okay? So that's kind of a quick summary of the broad strokes topics that you're going to want to understand. We'll obviously do some examples right now, but any questions on some of this latter stuff you want to talk about?
Can we talk about the spectral theorem and spectral decompositions again?
Okay. So the spectral theorem is the spectral theorem really is kind of a fancy name for the theorem that tells us that a matrix can be diagonalized, orthogonally diagonalized, precisely when it's symmetric, okay? So the spectral theorem tells us that, you know, if your matrix is symmetric, you can always find enough eigenvectors, your geometric multiplicity is always equal to the algebraic multiplicity, and therefore you can always diagonalize it. So it's kind of just the spectral theorem is just telling you that you can always diagonalize the matrix, okay? Then the spectral decomposition, remember, is if you have a symmetric matrix, we saw that you can basically split it up in terms of eigenvalues and eigenvectors in this way here. So the spectral decomposition is basically like this outer product form of the singular value decomposition, but where instead of having u vectors and v vectors, you just have and singular values, you just have eigenvalues and eigenvectors involved. So that was what the spectral decomposition was. Is that okay?
Yeah, it makes a lot of sense.
Yeah. So other questions?
So in the spectral theorem, is it a biconditional? If it's symmetric, then it's orthogonally diagonalizable?
Yeah. One implies the other, and then the other implies the one. Yeah.
Okay, cool.
Good question. All right. Any other questions before we do some example versions or sample exams? No? All right. So in the previous hour, we started a practice exam. This is the exam from last semester. So the practice exams and everything are posted on Learning Suite right now. So you can go and you can. I mean, I think I posted them last week sometime. So you can work through them, and just encourage you to do so. So I did the first. We only actually got through 2 questions. Last one. We'll hopefully get through a few more. If you want to watch sort of the discussion we had on these sections, I will post the videos to YouTube, to the same YouTube channel as I've been posting the other videos. So yeah, you can go through. If you missed sort of the first 2 questions in the earlier hour, you can watch those online. You can also, if you can't come to the 12 o'clock class, you can watch what we talk about there as well. So and I think I'm going to hold a review session on Thursday morning. I haven't quite figured out the time, but I'll announce that as well.
Quick question.
Yeah.
How long will those review videos be up on YouTube? Because I noticed that last time you took them down after like the test went up, I think. I'm not sure.
Yeah. So I took those down because the way that I did the recording is I didn't realize that it also recorded like everyone's faces. And so a student, actually a couple students reached out and were just not comfortable with their faces being online. So I took them down. I'm not recording any faces this time, or at least I hope none. Like I don't have the gallery view or anything open, so hopefully, as long as I can do it without breaking any laws, I'll post it up and just leave them up. So.
Okay, sounds good. Thanks.
Yeah. All right. So again, this is on Learning Suite. It's the exam from last semester, and we're on problem 3 right now. So let's look at this matrix here, okay? So question 3 is asking us to find the singular values of this matrix. So remember, in order to find the singular values of the matrix, you guys can probably tell me as well as I can. Remember what we do is we take A transpose A, and we find the eigenvalues of the resulting matrix. So there's not too much else to this question, I think, other than just going ahead and computing. So that's a nice one there. So let's multiply this. I hope it works out nice.
Would A transpose be -1, 1, or would it be 1, -1?
Oh, shoot. I went the wrong order. Yeah. Just wanted to make sure that you guys are actually paying attention. I have no way to know if you're watching or if you're, I mean, you could be doing all sorts of things. So I'll throw
yeah, we're here.
Yeah, I'll throw a few things in there just to make
Except
sure.
me. I'm asleep.
Oh, Josh is asleep. Okay. I can't tell if I'm not watching your faces now, so I don't know who's asleep, who's awake. I don't know what interesting virtual backgrounds people have. This is kind of a little harder for me here. So, so I'm going to take this dot this. So I'm going to get 2 in this corner. I'm going to get 2 here, and I'm going to get 0 here. I'm going to get 2, 2, and 0, and I'm going to get 0, 0, and 2. Okay. What's one quick thing I can do to check that I probably did this right? What should this matrix be?
Symmetric.
Yeah, it should be symmetric. And so if I've done it correctly, it'll be symmetric. And in this case, it is. So that's my matrix A transpose A. Now I just need to find eigenvalues for it. So the determinant of A transpose A minus lambda I is the determinant of 2 minus lambda 2, 0. Okay, now obviously I should do cofactor expansion probably along the 3rd column or something like that. This 2 minus lambda is in a plus spot. So I'll get 2 minus lambda times the determinant of 2 minus lambda 2 minus lambda. So this is 2 minus lambda. So 2 minus lambda times 2 minus lambda is going to be lambda squared minus 4 lambda plus 4. And then I think it's a minus 4 here. So my board work haven't left myself much room there. So if we sort of simplify, I think we get 2 minus lambda, lambda squared minus 4 lambda. So I think this factors to 2 minus lambda, lambda minus 4 times lambda. Did I do okay there? So lambda 1 equals 4, lambda 2 equals 2, and lambda 3 equals 0. So question, what should I notice about the eigenvector or eigenvalues that I found here? What should be true about each of them?
They're positive.
Yeah, they should all be non-negative. Some of them could be 0, but they should definitely never be negative. So these are the eigenvalues, and if I'm not careful, I might look at the last option and say, hey, these are exactly the values. Let's check this one off. But remember, the singular values are the square roots. So sigma 1 is going to be square root of 4, sigma 2 is going to be square root of 2, and sigma 3 is going to be square root of 0. And if I look at my list, it looks like the 3rd option has those all available there. Okay. So any questions on this example? This is kind of a straightforward computation, so not too much tricky going on there. But anyone have any questions?
The reason the values are non-zero is because
do you mean non-negative?
Yeah, non-negative. I mean, the reason the values are non-negative is because it's from a symmetric matrix, right?
Not even because it's symmetric. It actually is. You're right. I mean that the fact that they're all real numbers, it comes from the fact that it's symmetric, but the fact that they're non-negative comes from the fact that it's of this particular form.
Oh, okay.
So I mean, you could come up with a matrix that's symmetric and has negative eigenvalues like that. So negative eigenvalues come up in a lot of different matrices, but they never come up with a matrix that looks like that. I don't know if my red pen showed up there. Yeah.
Gotcha.
Okay.
Gotcha.
It's a little bit delayed. Sorry. All right. Any other questions here? Comments? Yeah, my office is cold. I don't usually get cold, but it's like I don't know, it feels cold today. Okay, let's look at problem 4 here. I think we're on good track to at least get through 3 questions, which will put us ahead of the last class. So let A be a 4x7 matrix with rank equal to 3. Which of the following have to be true? So whenever I'm in a situation like this, I like to kind of like draw what my matrix looks like, even just kind of like to show me what the shape looks like. So it's 4x7, so it has 4 rows, 7 columns. The rank is equal to 3. What does the rank being equal to 3 tell me?
The number of pivots.
Yeah, so the rank tells me the number of pivots. So I know that I get 3 pivots, and I don't know exactly where they are. But if I essentially know that I'm not going to get a pivot in every single row. I'm going to have at least one row where it's all zeros once I row reduce. I think I get one more 0 there too. Okay, so this is kind of like just like telling me what my matrix could look like. Okay, but I haven't really, I'm not saying that my matrix does look like this, but I'm just kind of trying to keep track of where the pivots will be, or at least how many pivots I have to have, okay? So let's go through this list of options here. The dimension of the null space of A, so the dimension of the orthogonal complement of the null space is equal to 4. All right, so this is a little tricky. I've got something about the null space of A perp. What does the null space of A perp mean?
Row space.
Yeah, so remember the orthogonal complement of the null space is equal to the row space, okay? So what this question is really asking me is the dimension of the row space of A, is that equal to 4? Is that true or not?
Not true.
It's not true, right? What's another word for the dimension of the row space?
Number of linear, and oh yeah.
Yeah, I think you're on the right track there.
Number of linearly independent columns is what I was going to say, but that is the rank.
Yeah, so another way to say the row space is just the rank of a matrix, or the dimension of the row space is just the rank of the matrix. So we're already told up top that the rank is equal to 3, so therefore we can see that this is not, the dimension of this is not equal to 4. Okay. 0 is a singular value of the matrix A. Can anyone tell me if that's true or not? That's a tricky one. I can't believe we put that on this last one. We were a little bit meaner back then. Maybe, I don't know. We'll see. So let's think through this. Okay, this will be a good exercise. Okay, so how do we find the singular values? Well, we saw above that we need to take the matrix A transpose A. We need to find eigenvalues, right? So if the matrix A is 4x7, okay, then that means that the matrix A transpose is 7x4. Okay, and so when we do A transpose A, we're taking a 7x4 times a 4x7, and we're going to get a 7x7 matrix. Okay. So what this tells me is when I take the matrix A transpose A, and I look for the eigenvalues of this matrix, I'm going to get 7 different eigenvalues. Well, maybe I'll write them like this. So I'm going to get a lambda 1, I'm going to get a lambda 2, I'm going to get 7 eigenvalues. Okay. Now these eigenvalues none of them are negative. That's one thing I know. And then from these 7 eigenvalues, I'm going to get my singular values. So sigma 1, sigma 2. Okay. So all this is to say, I just wanted to kind of figure out how many singular values should I expect. Well, I should expect 7 singular values. Okay. Now remember, we have this fact where the rank of a matrix is equal to the number of non-zero singular values. Okay, so therefore, because the rank of my matrix is 3, I know that exactly 3 of these things are going to be bigger than 0. So lambda 1 is bigger than 0, or sigma 1 is bigger than 0, sigma 2 is bigger than 0, sigma 3 is bigger than 0. But then everything else after that is equal to 0. Okay? Does that make sense? So the key to telling whether this is true or not is A, we have to figure out how many singular values we're going to have, and then B, we have to, by understanding the rank of the matrix, we know how many of them are going to be 0, how many of them are not going to be 0. Okay? So in this case, we know that we're actually going to get 4. We're going to get 4 0 singular values, and therefore the second option is true. Any questions on that one there? No? All right. So that was a bit of a trickier one. I'll give you that. All right. So let's look at the other options. The dimension of row A perp is equal to 4. Okay. So remember, row A perp, the orthogonal complement of the row space is equal to the null space. Okay. So this question here is really asking, is the dimension of the null space of A equal to 4? Is that true or not? And if it's true, can you tell me why?
It's true.
Okay, and why would it be true?
Because your null space is going to be equal to the number of like free variables you have.
Yeah, exactly, right? So remember, we have the rank theorem. The rank theorem tells us the dimension of the row space plus the dimension of the null space is equal to the number of columns. And in this case, that's equal to 7. So another word for the row space, the dimension of the row space is the rank. Another word for the dimension of the null space is the nullity. And so therefore the rank plus the nullity equals 7. Now the nullity, so this is the number of pivots, and this is the number of free variables. Okay. So there's a bunch of ways you can see this. I don't know. Can you guys see the bottom of the screen there? I can't see it underneath my the Zoom controls are blocking it. Can you see the word variables there?
Yeah, we can see it.
Yeah,
We can see it
Okay.
right now.
All right, it's just covered on mine, I guess. So because we know that the rank is 3, there's going to be 4 free variables because they have to add up to 7. I mean, again, you could just kind of count the number of pivots here and the number of free variables. But the key to this question is A, recognizing the row A perp is the null space, and B, recognizing that the dimension of the null space is just the number of free variables. So in both, so this is correct. Okay. Now we have a few other ones. So the dimension of the row space is equal to 4. Is that true or not? Well, it's not true because remember the dimension of the row space is just the rank, and the rank is equal to 3, so that's false. The dimension of the null space is equal to 1. Well, we actually just concluded above that the dimension of the null space is 4, so that's also not correct. And the dimension of the column space is equal to 3. Is that true or not?
That is true.
No, that's not.
It actually is true, because remember, even though the row space and the column space, so remember, row A is going to be a subspace of, is row A going to be an R4 or is it going to be an R7?
It's an R4, right?
Actually, it's an R7, right? Because if you look at our matrix, remember the rows, the row space is just the space spanned by the rows, right? Since there's 7 columns, these vectors all have 7 entries in them. These rows all have 7 entries in them. So the row space lives inside of R7. The column space is just spanned by the columns. It lives inside of R4, okay? So even though the row space and the column space live in different RNs, they'll always have the same dimension. Okay, meaning if one of them is three-dimensional, the other will be three-dimensional. Okay, and so the dimension of the row space and the dimension of the column space are always both equal to each other, and they're both equal to the rank of the matrix. So in this case, because we know the rank is equal to 3, we know that the dimension of the column space is equal to 3 as well. Okay. So any questions on this one? No?
Well, I think I figured it out on my own, but in the event that you have so the pivots don't mean that you can't have another value later on in the row, right?
Oh,
it just has to be something.
No. So like you're kind of wondering, well, how could the rest of this matrix be filled in?
Yeah, the rest of the matrix could be filled in so that the columns have some values other than just the one.
Yeah. So basically, you know that a pivot, if it's in reduced row echelon form, you know that the pivot is the only thing in its column. But for columns that don't have pivots, so you know that the rows that don't have any pivots will all be zeros. But the columns that don't have pivots, those can kind of be filled up with other things as well. Yeah.
So but in that case, you still have those. If you like take the transpose, it's still, you reduce them, and you still have a dimension of 3.
Yeah.
Okay.
Other questions? No? Okay. Well, that actually does it for time today. Like I said, I'm going to post the 2 videos here online. I'll also post the third video that I do at 12. You're welcome to come back at 12 if you want. I will go through those review slides again, but then I'll pick up where I left off here. We probably won't make it too far through these, but on Thursday morning, I'll have a review and we'll just pick right up where we left off. And on Thursday, we'll just do a bunch of review questions. So I haven't announced the time on Thursday. I have to kind of look at my schedule a little bit on Thursday. But we'll do some more review on Thursday. The Math Lab is also holding reviews Thursday afternoon and Thursday evening. So between my review sessions and the Math Lab, hopefully you'll get a lot of time to go through examples. But any other questions then before we sign off? And I will post those review slides in the next like 5 minutes or so. So just hang tight and they should show up soon. Any other questions before we sign off?
Do you want to see the virtual background I got ready for today?
Okay, so let me stop. Okay, I gotta see. Let me stop the recording and then we'll go there. All right. So if you want to sign off, you're welcome to, but I'll stop the recording now.